I mean, if you're doing a financial analysis, you're not doing a real net present value calculation, your priorities are going to be way out of whack.
Mm-hmm.
So if your discount rate for two different reward classes, let's say, within a game, should be different.
I haven't seen too much about that. Yeah, so the only things I can point you to are probably the conditional value at risk work and maybe some of the discussion in the GAE paper.
Okay.
I should probably start the... Okay, we're going to get started now. So today we're going to, again, have a two-part lecture. We had a little change of plans, so I'm actually giving today's lecture. But then on Wednesday, we'll have the first guest speaker. So today we'll have a two-part lecture. First part is going to be on advanced imitation learning and how we can combine imitation learning and reinforcement learning together. And in the second part, I'll talk about challenges and open problems in deep RL and sort of conclude this part of the course. And then on Wednesday, we'll have our first guest lecture by Igor Mardash from OpenAI. So I would very strongly encourage all of you to actually come in for that lecture. Igor does some really fascinating work at the intersection of multi-agent systems, natural language, and reinforcement learning. And he'll talk about some of his latest results. So I think that'll be really exciting, and you guys should all come in and ask him questions. But today we'll conclude sort of my portion of the class with these two components. All right, so if you think back to the second or third lecture in the class, we talked about imitation learning or behavior cloning. So imitation learning is a very simple way to acquire behaviors that can be represented, for example, by deep neural networks, and it's basically the supervised learning take on decision-making and control. So in imitation learning, you might have, for example, a human driver over here drive a vehicle. You record the images from the camera and the commands that the human executed. You take your data set, your training data, then you run your favorite supervised learning algorithm on it, and you get a policy that predicts actions conditioned on the observation. So this is very simple, kind of a standard supervised learning approach taken to decision-making and control. And we talked about how this has a few issues that we need to address, like distributional shift. But at a very high level, it's a simple and actually fairly reasonable way to get complex behavioral skills if you have the luxury of having lots and lots of demonstration data. And we saw how this could be used in some real-world settings. So you could get this to drive a car if you're feeling particularly brave. You could get this to fly a drone through a forest and so on. So there's some very compelling real-world results that indicate that these kinds of techniques really do work and do something very reasonable in complex open-world situations. In reinforcement learning, of course, we don't have the human data. We have to have a system that's continuously interacting with an environment, getting rewards, and then trying to learn from those. And with reinforcement learning, also, we can learn complex skills. We can have RL algorithms. This is Q-learning, learning to play Atari games. So again, we can do complicated stuff, but with starting from slightly different assumptions. So in today's lecture, what we'll do is we'll discuss actually the intersection of these two ideas, the combination of imitation learning and reinforcement learning. And to start on that, let's think about kind of how these two regimes for learning behaviors really compare. So there's the obvious one, which is that imitation learning requires something to imitate, so you need demonstrations. But the flip side of that is that reinforcement learning also, of course, it doesn't learn from nothing. It still requires some kind of signal to tell it what to do, which is the reward function. And in some cases, getting this might be hard. And in some cases, actually getting this might be hard. In some cases, it might be easier for us to get demonstrations. Imitation learning requires us to have some mechanism to address distributional shifts. So pure supervised learning, as we learned, is not actually something that's going to carry any kind of guarantees about getting effective behavior. We need to go a little beyond that. Reinforcement learning has to address the exploration challenge. So in reinforcement learning, the good thing is that you're figuring out what to do by yourself without a human telling you, but the bad thing is that you're figuring it out by yourself, which means that you need to explore. So you might have delayed reward problems, like Montezuma's Revenge, where you need a sequence of unlikely actions until you receive any signal telling you that you actually did the right thing, and that can be extremely challenging. Imitation learning tends to use simple and stable supervised learning algorithms. So many of you, when you were doing homework 2 and homework 3, discovered that setting up some of these algorithms correctly can be very challenging. Setting up supervised learning algorithms, by comparison, tends to be quite a bit easier. Whereas reinforcement learning algorithms can be potentially non-convergent or very tricky to set up or tune. Now, one of the big downsides with imitation learning is that pure imitation learning is only ever going to provide you a policy that's as good as the demonstrated behavior. So if you're trying to do extremely high performance superhuman driving and you only have access to driving data from an ordinary human driver, maybe you just can't do any better than that. Whereas reinforcement learning in principle has the potential to become arbitrarily good. So if it's a stable convergent optimization that's really going to hit that optimum, then it will keep getting better and better with respect to the reward until it really gets to the optimal behavior. So in principle, the kind of proficiency you can get from reinforcement learning might be quite a bit better than what you might expect from imitation learning. So now the question that we're going to think about in today's lecture is, can we get the best of both? So there are some things on the left and some things on the right. And sometimes, maybe we want something that's simple and stable, doesn't suffer from challenges with exploration, but still can become arbitrarily good, for instance. Can we kind of pick and choose these benefits and really get the best of both sides? And in particular, we're going to consider the setting where you actually have both demonstrations and rewards. So there are some cases where maybe getting the demonstrations is hard, some cases where getting the reward is hard, but there are some cases actually where you can get both, and what you're really concerned about is getting the best possible performance out of your system. So for example, if you want to get the self-driving car to drive, well, it's not a big deal to spend some time crafting a reward function. It's not a big deal getting hundreds of hours of human demonstration, because what you really want is the maximum proficiency out of your system. And actually, in many cases, if you're really after the best possible performance, if you're building, for example, a machine to play the game of Go against the world champion, and you have millions and millions of dollars at your disposal, maybe it's okay to get a bunch of demonstrations and a bunch of reward function and training data or experience from your policy to get the highest level of performance you can get. Okay, so one of the ways in which combining RL and imitation learning can help is by addressing this problem of distributional shift. So imitation learning, as I mentioned, suffers from distributional shift. Reinforcement learning does not, because reinforcement learning actually collects data from your policy. And in fact, the inverse reinforcement learning algorithms that we talked about are essentially doing that. The kind of adversarial inverse reinforcement learning that we covered in an earlier lecture, it actually combines imitation learning and RL, and the RL mechanism is actually the mechanism that adjusts distributional shift. So this is the diagram of the adversarial IRL framework that we covered before, where you have human demonstrations and you have a policy. The policy is trying to optimize some learned reward, and the reward is being modified so that the human demonstrations look like they have higher reward than the policy. This is addressing distributional shift because when this policy runs in the real world, it actually collects data that the machine would actually see when it acts. So in a way, the adversarial IRL approach can be viewed as an imitation learning method that addresses distributional shift, not by querying for additional human data, but by actually running reinforcement learning against an inferred reward function. So it already addresses distributional shift via RL, and this part is the kind of the forward RL part. That's the part that explores in the real environment and collects on policy data, and this part is the imitation learning. But it doesn't use a known reward function. So in IRL, we assume the reward is not known, and we're just dealing with the demonstrations. So next you might say, well, what if we actually already know the reward function? Can we do even better that way? So the simplest way to do this, and kind of the easiest to do out of the box if you have a good reinforcement learning algorithm and a good supervised learning algorithm, is to simply do pre-training and fine-tuning. So what that means is the following. So demonstrations can allow us to overcome exploration. They can show us how to do the task, but they might not get us to an arbitrarily high level of performance. So reinforcement learning is the mechanism that will allow us to then improve beyond the level of the demonstrator. So a very simple way to combine demonstrations and reinforcement learning then is to initialize your policy with imitation learning using your favorite imitation learning method, and then fine-tune with reinforcement learning to get to that arbitrarily high level of performance. And the reason that we expect this to work is that we expect that this initialization from imitation learning, if we did everything right, hopefully more or less does the task, just not incredibly well, which means that it probably would overcome the exploration challenge. It would allow us to observe the reward, and then we can maximize that with the reinforcement learning. Yes, there's a question?
Aren't we going to get stuck into a local minimum doing
Yep.
the imitation and
Yep.
reinforcement learning?
Exactly, yeah. So this is, I'll discuss that next, but this is exactly the problem with this approach. Yeah. But before I get into that, let me just write it out here because I think it'll help to see it written, and then we can compare it to other methods. So Specifically, the way such an approach would work is that you collect your demonstration data, and I'll denote it with SIAI. So without loss of generality, I'll just say that your demonstrations are tuples of states and actions. They might be arranged as trajectories, which is perfectly fine, but it won't matter here. Step 2, you initialize your policy with some supervised learning objective. A very good one is maximum likelihood, so just maximize the probability of those actions given the states. Step 3, run your policy pi to collect some experience. And step 4, improve the policy using that experience with any RL algorithm, and then repeat. Right, so that makes sense. This is the initialization, this is the fine-tuning. Now, an interesting side, actually, before I talk about an interesting side note, let me show you a little video of this in action. So this is a robotics example of this approach. And in the robotics setting, this kind of method is actually extremely popular. There, the initialization is typically done with something called kinesthetic teaching, where a person actually holds the robot and guides it through the motion, and that gives it the initialization. So this is a video of, in this case, Katerina Mulling, initializing her robot with a kinesthetic demonstration. The robot is then going to learn to play ping pong. So it takes a little bit of expertise to do this, but it's a great way to get some demonstrations. And of course, with other systems like an autonomous car, it's a lot easier to get this demonstration data. There's a question?
Yeah. So why would we expect the first 2 steps to help at all? Because that's just the original behavior cloning that we did, right?
So we would expect these first 2 steps to help if the problem itself has a very big exploration challenge, and you don't see any rewards until you have fairly reasonable behavior. So imagine this, this task, for instance. If we reward the robot every time it returns the ball, if we start from scratch and it's just waving the arm around in the air at random, it'll essentially almost never return the ball. If we initialize it with the data collected with this procedure here, then maybe it'll return the ball occasionally. Like, it might still not be perfect because of distributional shift, but it succeeds at least occasionally, and then it gets some gradient information for RL. Okay, one of the things that I think is kind of an interesting footnote here is to compare the structure of this algorithm to another algorithm that we learned before, which is Dagger. So Dagger, if you remember, addresses the distributional shift problem in imitation learning, because in Dagger, you collect additional data from your policy. So in Dagger, step 1 is to train your policy using your human data. Step 2 is to run the policy to collect some data. Then you ask a human to label, and then you aggregate, and then you repeat this process. And if you compare the structure of this algorithm to this method, it actually looks awfully similar. In both cases, you initialize with the human data, you run the policy to collect more data, and here you label it with rewards, whereas here you label it with the ground truth human actions. In fact, Dagger is exactly this procedure up here for a particular choice of reward function. So in Dagger, the reward function is the difference between the policy's actions and the human's actions. And you can actually show that if your reward function depends only on the difference between the actions, then Dagger and that thing over there are doing exactly the same thing. And just the process of collecting these labels is the process of evaluating the reward function. And just so happens that the special structure of this reward function yields a simpler training algorithm. Okay, so what's the problem with this approach? So there are a couple of problems, and one of which was alluded to before in the question. One problem is that this policy, when you initialize it, it can be very bad. It can be arbitrarily bad, in fact. So if you're driving your car and you have to drive it along the cliff, and there's a windy mountain road, if your initial policy makes a mistake early on in the training process, remember, with imitation learning, it doesn't know that a mistake early on is any worse than a mistake later on. If it makes a mistake early on and falls off the cliff, it doesn't matter what it does next. So as soon as RL figures out how to correct that mistake, it might have rendered that initialization completely useless. So in the process of correcting that initial mistake, it might completely wipe out your nice initialization, and you might get no benefit at all from the demonstrations. And this, of course, brings us to the second problem, which is that if the very first batch of data that you get from running your policy is very bad, not only do you have a bad policy, but you'll also destroy your initialization. So once you collect that really, really bad data, the RL algorithm will get gigantic gradients that will try very, very hard to fix that initial mistake, possibly at the expense of completely wiping out whatever knowledge you might have had. So in general, because of the distributional shift problem, and because there's no promise that your initial pi theta it has any kind of good performance at all, in general, this method can be arbitrarily bad in the sense that you might get no benefit from the demonstrations. It's still going to at least be as good as an RL algorithm because it's just running an RL algorithm for fine-tuning, but you might not get that exploration benefit if you wipe out your good initialization with a very bad initial batch of data. So can we avoid forgetting the demonstrations, still retain that benefit, and still have kind of a nice simple algorithm? That's what we'll talk about next. So one of the ways that we can incorporate demonstrations without forgetting them is to use off-policy reinforcement learning. So off-policy reinforcement learning allows you to incorporate data into the reinforcement learning process that was not gathered from your policy. And a very natural thing to consider then is to say, well, what if we use that as a mechanism to incorporate demonstration data? So off-policy RL can use any data. If we let it use the demonstrations as off-policy samples, maybe that can mitigate the exploration challenges. So maybe if we show it this data as an off-policy sample, maybe that can guide the learning process and substantially simplify the exploration problem. The demonstrations are provided as data in every iteration, so they're never actually forgotten. But the policy can still become better than the demonstrations because there's nothing forcing it to mimic them. So there are two ways that we'll discuss doing this. One is off-policy policy gradient with importance sampling, and the second way is off-policy Q-learning. So you can do policy gradient with demonstrations, and in order to do that, you need to incorporate off-policy samples, which means that for policy gradient, you have to do importance sampling. So importance sampling we covered at the end of the policy gradient lecture at the beginning of the course, and all you have to do is you have to add in these weights to multiply every sample, and the weights basically give you the product of the actions at the top under your current policy and at the bottom under the policy from which the data was gathered. And now the only difference is that when you sum over your samples, you're going to sum over all of your demonstrations and your experience from your current policy. Now, why is this actually a good idea? Like, there's this intuition that incorporating demonstrations is good because they simplify exploration, but more mathematically, why would we ever want to include anything other than on-policy samples? You know, in policy gradient, we're trying to estimate the return of your current policy and then take its gradient. So it seems like if you're trying to estimate the return of your current policy, the best samples to get are the ones that are actually from your current policy. So is there some mathematical explanation for why we might want samples that are not from our current policy if we're trying to estimate, let's say, the expected return or the policy gradient? And it turns out that there is. So you can actually derive an optimal distribution for importance sampling. And here's what optimal means here. Let's say that you want to estimate some expectation. You want to estimate the expectation of f of x under the distribution p of x. So p of x might be your policy, it's a distribution over trajectories, and f of x maybe is your reward. In general, in reinforcement learning, we're concerned with estimating expectation and taking their gradients. So if you want to estimate an expectation like this, one of the things you can say is that, well, I know I'm going to use importance sampling, so I'm going to sample from Q and re-weight by P over Q, and then I'll ask the following question. How should I choose Q in order to have the lowest variance estimate of this expectation? So if I'm given a budget, I have n samples, what is the best distribution Q that I can use, given that I'm going to be estimating like this, in order to get the lowest possible variance? And it turns out that the optimal choice in that case is not to use P. The optimal choice is to use a distribution that's proportional to P times the absolute value of F. And there's a very natural intuition to this. If F is very, very small, almost everywhere, and very big in one place, you really want to sample that one place, otherwise you're not going to get a good estimate of the expectation. So the best sampling distribution should have high reward. We can illustrate this graphically like this. Let's say that our policy is this little Gaussian bump. And let's say that the reward function is a big spike like this. Now, if we just draw samples from this Gaussian bump, maybe we'll miss this spike completely. And we'll just get a bunch of samples with reward 0, and our policy gradient will be completely wrong. If we had computed the full integral, the intractable integral of the expected gradient, then we would have seen this bump and we would have figured out that we need to increase its probability. But if we draw random samples and we don't sample that bump, then we won't know where to move our policy. So it's a lot better if you had some distribution that would actually pick up on this spike, even if it's not the same as your current distribution pi theta. You would actually have a lower variance estimate. So this is the mathematical explanation for why incorporating good data, for example, demonstration data, into policy gradients can actually give you a better policy gradient. Okay, so how do we construct the sampling distribution? So there are two problems. Ignore that box for now, I'll come back to it. There are two problems that we need to address in constructing the sampling distribution if we want to incorporate demonstration data. The first problem is, which distribution did the demonstrations come from? So if we draw data from our current policy, we know what distribution came from. It came from pi. Pi has some representation like a Gaussian. We can evaluate its densities. But if we've got demonstrations from a human, we don't necessarily know what policy they had in their head, and we don't know the probabilities of those demonstrations. So we have to make something up. And we have a few options about how to make something up. They're all, they're all a little bit lame, but they'll work reasonably well. So one option is to use supervised behavior cloning to approximate the demonstration distribution. So you can say, okay, I don't know the demonstration distribution. Why don't I fit something with behavior cloning and just pretend that those are the densities? It's not a great option. It'll introduce some pretty nasty bias in some cases, but it will work in a pinch, and it's pretty simple. Another option is to assume a very simple distribution for the demonstrations, which is this kind of Dirac delta distribution, to say that the probability of some trajectory under the demo distribution is 1 over n if it's within the data set and 0 otherwise. This is a very peculiar distribution. It's going to have density values that are very different numerically from densities under your policy, but it's very nice because it doesn't really assume anything else about the demonstration distribution other than what you can get from the data. If you're going to use option 2, one thing that's pretty important is to use what's called self-normalized importance sampling, which means that instead of weighting your samples by the importance weight and then normalizing them by the number of samples, you actually normalize by the total importance weights, which means that the importance weights are essentially constrained to sum to 1. So this kind of importance sampling, this is kind of the classic version, which is unbiased. This one is actually biased in expectation but consistent, but it tends to work a lot better when essentially like the units of P and Q are very different. If Q is a collection of Dirac deltas and P is densities under a Gaussian, this version tends to be a little bit more stable and in general has lower variance. Problem 2, what do we do if we have multiple distributions? So over here, when we compute these importance weights, we take pi over Q. Pi is our current policy. Q is the distribution that the data was sampled from. But the data now was sampled from multiple different distributions. Some of the data came from the demonstrations, and some of it came from maybe our previous policy. So how do we construct Q if we have multiple distributions? There's a very simple solution to this, which is called the fusion distribution. So you essentially say that Q of x is the sum over all the Qs that you've sampled from divided by the number of those Qs. This has a sort of an interesting implication, which is that if you have multiple distributions that created your data set, you need to actually evaluate the probability of every single data point under every single distribution. So if you have maybe demonstration data and data from a couple of your previous policies, every single trajectory needs to be evaluated under every single distribution in order to form this fusion distribution. But other than that, this is a very reasonable way to tackle this problem. So there's two ingredients that we need. We need some way to figure out the distribution of the demonstrations, and we need some way to fuse multiple distributions into one so that we can incorporate all the data into our policy gradient estimate. Okay, does anybody have any questions about importance sampling and demonstration data? Yes?
For the fusion, it would seem like if I sample much more often from one distribution than another, then shouldn't it have a weight that reflects?
Yeah, so this is a good question. It's an oversight on my part. So this assumes that you have the same number of samples from all the distributions. If you don't, then you need to put, instead of 1 over m, you put a weight on them and have the weight sum to 1. Yes?
So the importance sampling ratio is a ratio of two probability distributions, which means it's basically unbounded. It can get very close to 0, very big.
Yep.
Can this somehow break the convergence of the algorithm, or? Oh,
absolutely. So formally, what this issue amounts to is that if you have, if you have extremely large or extremely small importance weights, it actually blows up the variance of this gradient estimate. So the optimal importance sampling distribution that I had on the previous slide, that's the distribution that will minimize the variance. If you're very far from that distribution, you might actually get extremely high variance. This trick, to use self-normalized importance weights, reduces variance at the cost of introducing a little bit of bias. There are a bunch of other tricks for reducing variance in importance sampling. One of them is to truncate the importance weights, to clip them either on the top or the bottom. And there's a collection of other fancier techniques. But in general, that's actually the #1 reason why importance sampling is not more popular, is that you do get these very degenerate weights. And the degeneracies actually manifest themselves in slightly different ways. So over here, they manifest themselves by giving you extremely ill-conditioned gradients, ones that either blow up or shrink. And over here, what you end up getting is, if you have a very large or very small weights, is that all but one of the samples will essentially go to 0. And then you're essentially just doing a one-sample gradient estimate, which is still going to be reasonably well behaved. It's just going to be a very poor estimator. Yes?
In the case the Q is all deltas, that's the same as just having the sum only over the Qs.
That's right, yeah.
Right?
Yeah, so there's a little degenerate case there where if you use this version, then even though you're summing over 2 distributions here, one of them is doing nothing. Okay, so let me show you a little video clip of this method in action. So these are a bunch of little Mujoko benchmark tasks, very similar to the ones that you did in homework 1. And this is trained using that method up there with demonstration data incorporated as additional samples into a policy gradient estimator. And these are standard kind of simulated benchmarks. This one is actually a 3D humanoid where the demonstration data comes from motion capture of a human. And then that motion capture is incorporated as additional samples into the policy gradient. There's a little bit of additional magic to actually make it possible to do that with actions, which is described in the paper, but that's basically the high-level idea. Okay, so that's policy gradient. Now, there are other off-policy algorithms we could use, and we could think about how well those would work. So we could, for example, imagine using Q-learning with demonstrations. Q-learning is already an off-policy algorithm, so we don't actually need to bother with importance weights at all. It will work with off-policy data out of the box. So there's a very simple solution, which is you just drop your demonstrations into the replay buffer and then run the standard Q-learning algorithm that we learned about. So this is the standard Q-learning algorithm we learned about, or at least one form of it. You collect some data by running a policy, add it to your replay buffer, sample a batch, take your gradient, and now the only change is that up here you'll initialize your buffer to contain the demonstration data. This is a very simple approach to incorporate demonstrations into Q-learning. This is a paper that actually does a variant of this called Leveraging Demonstrations for Deep Reinforcement Learning something or other. And here they actually use DDPG, which is a continuous variant of Q-learning. So there they have the Q function network, and they have a separate network that's trying to maximize the Q function. And they evaluated this on a number of simulated and also real robotic manipulation tasks where the demonstrations show the robot how to perform the task at some moderate level of proficiency, and then reinforcement learning is used to increase that level of proficiency. All right, now let's talk about the problems of these two methods. I've already alluded to some of the problems, but let's dig into them a little bit more. So with an importance sampling, the trouble is that using these importance weights is kind of the recipe for getting stuck. Importance sampling, especially if you initialize the policy with supervised learning, will do a pretty good job of mimicking the demonstrations. And the failure mode, oftentimes, is that it has a very, it has a lot of trouble actually getting past the demonstration. It has a lot of trouble improving on the demonstrations with the additional importance sampled reinforcement learning. And the reason for that is the degeneracy in the importance weights. So this is the form of the estimator again. And one of the things we can do, let me explain this plot here. One of the things we can do is we can plot a little picture like this where the red dots are samples. The horizontal axis is your state. And what the blue curve is showing is the estimate produced by importance sampling of the value of a particular state. So the idea is that, okay, these red dots, you can kind of extrapolate from them and figure out there's something really good going on down here. This is cost, so lower is better. There's something really good going on down here and something really bad going on up here. So a good algorithm would probably look at these samples and would decide, well, I want to be somewhere in this region over here, right? The trouble is that if your algorithm is currently over here and you're computing a gradient of this curve, there's a big flat plateau between here and the place where you want to go. And the reason for that big flat plateau is because these importance weights, as they get sharper and sharper, they essentially have almost no gradient. They act almost like a nearest neighbor measure. So if you're closer to these bad samples, it'll tell you, oh, your value is bad. As soon as, the reason this drop happens right here, this is exactly the halfway point between this sample and this sample. So once you go past that halfway point, now you're closer to the good sample and tells you, oh, now you're good. But this nearest neighbor function becomes almost non-differentiable as the magnitude of the probabilities gets larger and larger. And the magnitude of the probabilities gets larger and larger because it's actually exponential in the time horizon. So this picture, this is for a single time step. We can also expand this picture in time. So at the back here, this is 1 time step. At the front, this is 20 time steps. And because the weights get sharper and sharper exponentially in the time horizon, as you move further and further in time, basically as t over there gets bigger, these plateaus get flatter and flatter. So the longer your trajectories are, the flatter these plateaus will be, and the less informative your gradient will be. So importance sampling, as your densities get larger and larger, and they always do because it's exponential, starts to look an awful lot like nearest neighbor, which is not really differentiable. So that's the trouble, is once you have these good demonstrations, you essentially get stuck in them, and it's very hard to get good gradient information. You can play all sorts of games to try to clip the weights or to soften the weights, which will actually help alleviate this issue, but at the expense of introducing some bias. Okay, does anybody have any questions about this? Okay. So Q-learning also has some problems. They're very different problems, however. So with Q-learning, the trouble is that good data is just not enough. Q-learning is trying to estimate a Q function. And a Q function is not actually all that useful in terms of its absolute values. It's useful in terms of the relative values it assigns to different actions. So the trouble with Q-learning is that if you only see good actions, it's actually very hard to figure out which actions you should take. Let's again try to understand this visually. Let's say that this is the true Q function. This is Q star. So Q star, the x-axis here is action, and the vertical axis is value. So Q star clearly shows us that this is the best action, right here at the peak. And let's say that your demonstration is a very good demonstration. It actually gives you that action. The trouble is that if that is the only sample that you have, Q-learning cannot learn what the true Q function is. It's essentially trying to fit a curve through this point. So this is a very good curve to fit through this point. This is an equally good curve. And there's simply no way to understand from just seeing this good action which actions are better and which actions are worse. So in order for Q-learning to succeed, it needs to see both good actions and bad actions. If it only sees good actions at that state and doesn't have any essentially counterexample, it doesn't have any way to know whether that action is any better or worse than any other one. So for this reason, simply dropping the data into the replay buffer doesn't always succeed. Okay, so far, we talked about a number of methods to combine reinforcement learning and imitation learning. We talked, of course, about pure imitation, which is easy and stable, but it suffers from distributional shift. And it has no chance to get better than the demonstrations. We talked about pure reinforcement learning, which is good, healthy, unbiased reinforcement learning. It can get very, very good because it's really optimizing your reward, but it has a challenging exploration and optimization problem. We talked about initialization and fine-tuning, which is almost the best of both worlds, but suffers from this problem that if your initialization is not very good, you'll essentially forget it, and then you won't benefit from the demonstrations. And then we talked about pure reinforcement learning that can incorporate the demonstrations as off-policy data. And that is good, healthy, unbiased reinforcement learning, but the demonstrations don't always help for fairly technical reasons associated with a particular reinforcement learning algorithm that you use. At a high level, this problem basically amounts to saying the way reinforcement learning incorporates data is not as simple as the way supervised learning incorporates data. So in supervised learning, it's much easier for it to make use of good data than in a reinforcement learning algorithm. And there are some fairly deep mathematical reasons for this having to do with the particular nature of the reinforcement learning objective. But the short version is that objectives like pure imitation learning are just easier. So can we strike some kind of compromise? Over here, we're trying to get an unbiased reinforcement learning algorithm. If we're willing to admit a little bit of bias, can we strike a compromise and have a nice, easy supervised learning objective and still get the benefits of reinforcement learning? So that's the last category of methods that we'll cover, which are essentially reinforcement learning algorithms that incorporate imitation learning as an auxiliary objective function. So we'll say, okay, we have an imitation learning objective, which is maximum likelihood. We have or some variant of this. We have a reinforcement learning objective, which is to maximize the expectation of the reward, or some variant of this like maximum entropy. And we'll just staple them together, put a weight on here, and just say pick lambda, and you'll have reinforcement learning plus supervised learning. So you'll simultaneously optimize both objectives with some weighting between them that trades off one versus the other. You need to be very careful in choosing that weight because if you set it to too low, then you're doing pure reinforcement learning. If you set it too high, then you might not improve beyond the demonstrations. But it can actually work fairly well if you're willing to do a little bit of tuning. So this is a method that actually I showed in a previous lecture, and I think Josh also showed by Rajaswaram et al. Called learning complex dexterous manipulation. And this method basically takes a standard policy gradient and it adds it to a standard maximum likelihood objective. And remember that policy gradient and maximum likelihood look awfully similar. Policy gradient, you can think of it as just the maximum likelihood gradient weighted by the advantages, and the maximum likelihood gradient is just weighted by 1, or in this case, a weight. And the weight just tells you how much you prefer demonstrations versus reinforcement learning. And that turns out to actually work fairly well. This is a video that I showed before with the in-hand manipulation. The demonstrations here are obtained by a human using what's called a cyber glove. It's a glove that allows you to capture the movements of your hand. And that's then used together with a reinforcement learning algorithm to allow a simulated robotic hand to perform a variety of different tasks. So this kind of method can allow you to improve beyond the demonstrations because of this first term, but you never really forget the demonstrations because of the second. The trouble, of course, is that how far you can improve is limited by your ability to tune that weight. So if you tune the weight to be too large, then that might prevent reinforcement learning from really moving away from the demos. There is another paper that I want to cover here. This is by Hester et al. Called Learning from Demonstrations, I think, for sample-efficient reinforcement learning. And this is a method that combines Q-learning with actually a variety of auxiliary objectives. So they're going to be concerned with playing Atari games using human demonstrations, and they have an objective for their demonstrations. It's a little different from the maximum likelihood objective. This is actually a kind of a max margin objective. It says that the Q values of the demonstrated data should be larger than all the other Q values by the largest possible margin. So it's still a supervised learning objective, but a slightly different one. Then they have a standard Q learning loss. They also have like an n-step Q learning loss. And they also have a regularization loss to do L2 weight decay, because why not? Like, I guess the more the better. But the short version is that it's basically, the main action is this thing, which is this margin loss for demonstrations, and these two, which are basically two different but standard reinforcement learning losses. And the kind of tasks that they're testing this on are Atari games. So the shiny blue curve, that's their method. That's using demonstration data. And then probably the, oh, I see. So the pink one, this is if you just play back the human's actions, because the Atari games are deterministic. And then the other ones are kind of different ways to incorporate demonstration data. So these are all doing some kind of demonstrations, except for the black curve, this one, the no supervised loss. That's basically their method, but without the JE. So that one is no demonstrations. And unsurprisingly, they get the most benefit on tasks like Montezuma's Revenge, where exploration is extremely difficult. So this is basically illustrating that if you do incorporate the human demonstration data and you do it in a way that prevents forgetting, you do actually get that big exploration benefit. Yes?
So actually I have a question on the previous slide.
Mm-hmm.
So when you're trying to incorporate just imitation with this extra loss,
Mm-hmm.
So are they running through the exact same scenarios that were demonstrated? Because if it's trying something
Yeah.
that hasn't been
Yep.
demonstrated, then what's even...
So this is a very good question. Is what are the environments in which they're doing this? So this is actually an important point that doesn't really come up in the other paper because the Atari games are deterministic. Here, the initial poses of the hand and the initial positions of the objects are randomized. The trick is that the demonstrations, they don't necessarily come from the same configuration of the objects, but those configurations are sampled from the same distribution. So in RL, every single trial, you sample a different initial state, which here corresponds to a different positioning of the objects. And the demos are also sampled from a different positioning of the objects. But they're all from the same distribution, so as far as the algorithm is concerned, these all look like samples from the same initial state distribution. Okay. So what's the problem with this last approach? Well, it's more or less exactly what you expect. You need to tune the weight So you get this benefit of this nice, easy supervised objective and a nice, simple reinforcement learning objective, but you need to tune the weight between them. The design of the objective, especially for imitation, takes a little bit of care. So there's a reason why the Atari paper used this margin-based loss, because they found that it worked better for them than max likelihood. The algorithm becomes somewhat problem-dependent, so the particular way in which you combine these two terms, and especially the way that you weight them, might depend on the particular problem that you're trying to solve. And in general, it takes a little bit more care to really set this up. But the benefit is that you typically get a much simpler, much more well-conditioned optimization problem. So we talked about pure imitation learning, we talked about pure reinforcement learning, initialization and fine-tuning, reinforcement learning with demos as off-policy data, and lastly we covered this hybrid objective where imitation acts as a kind of auxiliary loss function, which, like initialization and fine-tuning, it's almost the best of both worlds. It has no forgetting, but it comes at the expense of no longer being pure RL, which means that it might be biased, you might not improve the reward to be arbitrarily large, and it might require a lot of tuning. But in practice, this can be a good way to get things to work if you're willing to spend a little bit of time setting things up. Okay, does anybody have any last-minute questions about combining reinforcement learning and imitation learning? Okay, let's take a 3-minute break, and when we come back, I'll talk about challenges and open problems. All right, let's continue. So in the last portion of today's lecture, I'm going to talk about some of my thoughts about open problems in deep reinforcement learning, some outstanding challenges, and hopefully also get you thinking a little bit about the kind of problems that you might want to tackle, either in your final project or if you're considering continuing research in this field, the kind of challenges that you might want to take on in your work. So to start with, let me summarize a few recent papers in deep reinforcement learning, going back maybe 5 or 6 years, and point out three main themes in kind of the sort of things that people have really made progress on. And I don't mean to suggest that these are necessarily the best papers, but they're kind of a sampling of papers across different areas of deep RL that have, that are generally reasonably well known. So One of them, this is might not actually be well known, but is a paper that was actually one of the first real modern deep RL papers by Lang and Reed-Miller on reinforcement learning with raw visual input, which used a combination of low-dimensional embedding and Q-learning. This is the guided policy search paper that I mentioned a few times. This is the original Atari Q-learning paper. This is trust region policy optimization. It was one of the first policy grading methods that really worked with complex, high-dimensional deep neural networks. This is the end-to-end visuomotor policies paper on real-world vision-based robotic control. This is the DDPG paper, which showed that you could actually get actor-critic methods to work very well on complex, high-dimensional tasks. The AlphaGo paper, which showed that you could actually tackle really complicated problems and exceed human levels of proficiency. And this is a paper from Carnegie Mellon that showed that you could actually collect large amounts of very diverse data on a real robotic platform and get a robot to generalize to new objects it hasn't seen before through a very simple kind of reinforcement learning. If you haven't read these papers, I highly encourage you to check them out. They're all quite interesting. But the main point for today's lecture is that they really, for each of these papers, they address one of three themes, and a lot of their impact is due to the degree to which they address these themes. So one of the really important themes is improving stability, meaning getting algorithms that, on paper really ought to work, getting them to actually work on complex problems, typically with a variety of mundane but very important computational tricks. So in the case of this paper, it was the low-dimensional embedding. For the guided policy search method, the improvement was along efficiency, trying to get reinforcement learning algorithms that can learn with a number of samples that's much more practical for realistic applications. For the Q-learning here, again, most of the main innovations that made this work compared to previous applications of Q-learning were improvements to stability, things like target networks and experience replay done in just the right way to enable the method to actually learn. And same with the trust region policy optimization. Here again, the story is about efficiency, and also with the actor-critic method, one of the big improvements of this algorithm over this one was substantially better sample efficiency, which is why there have been actually real-world applications of directly using this type of method on real systems because it's actually efficient enough to use. And then with these last two, the big innovations really center around scale. So the fundamental ideas underlying the algorithms in both of these two papers were actually reasonably well known. The trick comes in scaling up those ideas to really work on complex problems with extremely large amounts of experience and extremely large amounts of data. So I would say that really most of the challenges in deep RL today center around these three themes: stability, efficiency, and scalability. And I'll talk about each three of these, point out some challenges, and a few thoughts about the direction some of that could go. So let's start with stability. These problems range all the way from the very mundane of how you actually run your algorithm, how you get it to work, all the way to the much more advanced research questions of how do you design better algorithms where these things might someday no longer be such a big problem. So devising stable RL algorithms is very hard. Typically, almost all the algorithms that we use have some kind of problem that severely limits their stability. So with Q-learning or value function estimation, the problem is that fitted Q or value function methods with deep neural networks are not actually contractions, and therefore they don't have a guarantee of convergence. So we covered this in lecture, if you remember this picture, that says that once you compute the Bellman backup, you improve with respect to the infinity norm, and when you then take a gradient step, you improve with respect to the L2 norm, and composing those two things doesn't necessarily allow you to get closer to the optimal value function with respect to any norm. So this is a big problem, and in practice, there are a lot of parameters that affect the stability of these methods. Basically, the way that you overcome this issue is by tuning lots of knobs until it works. And the knobs are things like the delay of the target network, the size of the replay buffer, how you clip the gradients, the sensitivity to learning rates, exploration, and so on. Many of these things have a tremendous effect on whether or not these algorithms actually converge to a good solution. Policy gradient methods they don't necessarily suffer from this problem, but they have other problems. So the trouble with policy gradient methods is they have a very high variance gradient estimator. And a lot of the pain and suffering that we go through with policy gradients is to get the variance of that estimator down to a manageable amount so that we can actually get improvement. This might involve, for example, using very large batches, which is where the sample efficiency problems come in, using very complex baselines, using clever control variates, and so on. The kind of parameters that we might want to tune are things like batch size, learning rate, and the design of the baseline. And even though there's typically fewer parameters to tune here and it's a bit easier to get these things set up, it does take a bit of care, especially if you want to get good sample efficiency. Model-based RL algorithms also have their share of problems. So the model class and the way the model is fitted very, very strongly affects the performance of the algorithm, as many of you probably discovered in homework 4. Optimizing the policy with respect to the model, if you want to actually learn a policy, is typically non-trivial. You can do it through backpropagation through time. You can do it using other techniques. But this is not by any means sort of a solved thing where there's just an off-the-shelf solution. So with model-based, there's also a number of big challenges. Let's talk about hyperparameters a little bit more. So one of the things that until we invent really stable, really effective algorithms that just work out of the box every time, until that happens, we have to figure out how we're going to deal with all these hyperparameters, because setting them up correctly oftentimes has a really huge effect on the performance of your method. So it's a good idea to get used to running multiple hyperparameters. For your homeworks, oftentimes we actually gave you good hyperparameter settings out of the box. Some of you sometimes implemented the algorithms a little differently, in which case our hyperparameters didn't work for you anymore, and then you had a really fun time trying to tune them, and that was probably pretty unpleasant. And if you develop new algorithms, you basically have to do this all the time. So one of the ways that you can do this is you can get used to running code where you always fire off your jobs with an array of different hyperparameters in parallel. So if you want to tune your learning rates, maybe you set up, well, I don't know what my learning rate is, so I'll always run a sweep across 5 different learning rates. Grid layouts for hyperparameter sweeps are okay if you're sweeping over 1 or 2 parameters. So if you're, let's say, sweeping over learning rate and maybe exploration variance for a continuous task, maybe you run all combinations on a 2D grid. But if you get to more than 2 parameters, this becomes really intractable. A random layout for hyperparameter sweeps is actually almost always better. It's just a little bit less interpretable. But if you have to sweep over too many parameters, it becomes the only viable option. One illustration that I'd like to show here to motivate why a random hyperparameter sweep might be better, this is borrowed from Yoshua Benjo, is to kind of graphically illustrate this. So let's say that you have 2 hyperparameters. And maybe you guessed wrong. There's one hyperparameter that's really important and another one that really doesn't matter. So this one up here has a big effect on performance. You can see there's a big hill here. And this one you thought it mattered, but it actually doesn't. It has almost no effect on performance. So maybe on your particular problem, the learning rate has a huge effect, but the exploration constant has minimal effect. And now you just fired off 9 jobs on maybe AWS or something. And this was the layout of the parameters for your 9 jobs. Now, because this unimportant hyperparameter has almost no effect on performance, in effect, you got 3 samples out of these 9 jobs along the important hyperparameter. If you had arranged your hyperparameters randomly, if you basically randomly sampled values of these 2 parameters, then you would see that, yeah, the unimportant hyperparameter is unimportant, but now you have all these samples on your important hyperparameter. So all 9 actually have a different setting, and you've learned a lot more about how to choose that value. So this is in 2D, and if you move to higher dimensions, then the grid setting basically becomes completely intractable. And don't forget about the random seed, too. So reinforcement learning algorithms are self-reinforcing, and they very likely will get into local optima. So running multiple random seeds is very important to understand if your method is really working, and also to actually evaluate how well it's working. And don't assume it works until you've actually tested some number of random seeds. And also remember that your random seed is not a hyperparameter. So you're not trying to choose the best random seed. You're trying to find settings that will work. Because if you then want to get this thing to run in the real world, you don't get to choose the random seed for the quantum wave function, right? Now, the story with random seeds is actually a little bit more complex than simply saying, well, let's run like a couple of them. Here's a little learning curve. The vertical axis is the reward function, and the horizontal axis is the number of time steps. So there's 2 million time steps over here. And there's 2 algorithms here, and these are going to be anonymous algorithms. We're going to call them the orange algorithm and the blue algorithm. And some of you may have read this paper, but for those of you that haven't read this paper, how many of you think that the orange algorithm is better? Yeah, so it looks better, right? There's even a standard deviation plot, right? So it turns out this is actually 2 runs of the same algorithm. This is TRPO and the half-cheetah task. And in fact, it's run for multiple random seeds. So these are actually averaged over 5 separate runs. So yeah, we should be a little careful about that. And we have to also remember that when we read research papers on this topic, there is an obvious publication bias, which is that people will run these things until they work, and then they write a paper about it. So remember this kind of picture, and remember that you really need to, if you want a real reliable answer, you need to be pretty rigorous about these, yes?
But But this might be a real effect, might be a property of the optimization landscape, right? Like,
Yeah.
From detractors.
Yes, it might, and in fact, it very likely is. So another very useful thing to do, and I wish more people would do this in their plots, is to actually, instead of just visualizing the variance, actually show what the different runs did. Because you will very often see on tests like this, there will be a bimodal distribution where there's some good runs and some bad runs. Okay. So there are a number of challenges with hyperparameters. Of course, we can't run hyperparameter sweeps in the real world. So if you develop an algorithm and it works very well, but it only works very well if you tune the hyperparameters meticulously for a single task, well, you have to remember that if you then want to use it for something useful, you have a few different choices. You could, for example, try to tune your hyperparameters or even train your entire policy in a simulator. But then the question is, how representative is your simulator? Sometimes it's pretty good, but very often the answer is it's not very representative. And even things like hyperparameter settings might not transfer across from simulation to real-world problems. And if you have an algorithm that really relies on a very large hyperparameter sweep, that might be fine. But you have to remember that then, if you're looking at the actual sample complexity of that algorithm for a real practical real-world problem, it's really the time to run the algorithm times the number of runs to sweep over the hyperparameters. Which, by the way, is not an unreasonable thing to do. So this amounts to essentially a kind of stochastic search plus reinforcement learning approach, which is a very reasonable way to solve a problem. You just have to remember that it's increasing the number of samples that you need by quite a bit. So it's in effect stochastic search plus gradient-based optimization, which is not a bad idea, actually. But it might also be very nice to think about whether we can develop more stable algorithms that are less sensitive to hyperparameters, where it might be a lot more practical for us to be able to get good solutions by running them only once. So what can we do? Well, we can look at algorithms with favorable improvement and convergence properties. So far, we don't have any algorithms that are good enough with this respect, but there are a few efforts in that direction. So the original TRPO paper actually discusses a potential improvement guarantee. Of course, in practice, that improvement guarantee ends up being very costly in terms of the number of samples. There's some work on what's called safe reinforcement learning or high confidence policy improvement, which amounts to introducing a statistical significance test on whether you have enough samples to guarantee with high confidence the improvement of your policy. So if you're interested in that, check out some work by Philip Thomas. There are also algorithms that adaptively adjust their parameters. So for example, an algorithm called QProp by Shishan Gu adaptively adjusts the strength of a control variate or baseline based on the correlation between that control variate and the empirical returns. And there's a few other methods in this category too. But really, there's more research that's needed here. And I think oftentimes the trouble is that developing more stable algorithms is not really a great tool for beating the benchmarks. Because if you're evaluating on your ability, on your best tuned hyperparameters, you might not actually do the best in terms of beating the benchmarks. But it's absolutely essential to actually make your reinforcement learning a viable tool for real world problems. So if you're working on research in deep reinforcement learning, I highly encourage you to think about how you can evaluate the stability of your algorithm or include a plot in your paper that studies its stability or its sensitivity to hyperparameters, because that's really, if we want to make these algorithms useful for real world use, that's an essential thing that we'll have to figure out. All right, let's talk about sample complexity next. So in an earlier lecture, I went through this picture discussing the sample complexity of different algorithms. And let me just very briefly recap this. So in this diagram, we have the least efficient algorithms at the top and the most efficient algorithms at the bottom. Efficient here means number of samples to achieve a certain level of performance. And unfortunately, this isn't a head-to-head comparison. This is sort of pieced together with circumstantial evidence, so it wouldn't hold up in court because different algorithms compare on different problems. But this is sort of my best effort to piece things together, typically using the half-cheetah task, because that seems to be the most popular one. And the story is more or less this, that if you have a gradient-free method, so we didn't talk about these too much, but this would be something like natural evolution strategies or CMAES. These tend to be about 10 times less efficient or 10 times more sample hungry than fully online methods like A3C. So this is a plot where someone is evaluating A3C and finds that it takes about 100 million steps to solve the half-cheetah task, which is about 15 days of real time. This in turn is 10 times less efficient than good policy gradient methods like TRPO, which take about 1.5 days of real time to solve the half-cheetah. That in turn is 10 times less efficient than things like DDPG and NAF, which take a few hours of real time. And in fact, a number of experiments on real physical systems confirm this, that it takes a few hours of real time. These are in turn 10 times less efficient than model-based methods like GPS, which in turn are 10 times less efficient than what's called shallow model-based RL methods. So these are RL methods that are using things like Gaussian processes. So this is circumstantial evidence, but it's a reasonable kind of rule of thumb guess as to sample efficiency that you incur a hit of about 10x as you go up the in line here. There's a question?
But how do they compare in terms of performance? So not necessarily a faster or better.
Yeah, that's a good question. So here I'm only talking about sample complexity. That does not necessarily address performance. So for example, if you try to solve the half-cheetah task using a Gaussian process, you just wouldn't get a good solution. Right? So this is sort of subject to the kind of problems these methods can solve. How do they stack up? And the other dimension, by the way, that I'm not even talking about here is wall clock time. So if you don't care about sample complexity and you just care about how long things take to run a cluster, then typically this picture is actually flipped. So typically there, actually, the GP things are the most expensive computationally. And the reason that people would actually care about things like gradient-free methods is because if you parallelize them enough, they can actually take less time in a very fast simulator. So here I'm just talking about sample efficiency. With wall clock time, it's usually upside down. Now, what about more realistic tasks? So these are relatively simple Mujoko benchmark tasks. In reality, you also get a big cost that you have to pay for dimensionality. So if you look at something like trust region policy optimization on the half-cheetah, it takes about, this is 8,000 episodes, which is about 8 million steps. And if you look at the same algorithm on humanoid, which is a 3D humanoid simulated robot with 50-something dimensions, there's a 10x increase in the number of samples that it requires. So now it goes up to 80,000 episodes or 80 million steps. So not only is it expensive, if you then scale up the dimensionality, it becomes a lot more expensive. You also pay a big cost typically to using raw images. So if you're learning directly from low-dimensional states, things work OK. If you're using raw images, especially with a non-policy method that has to take one gradient step for every single batch of data that is collected, optimizing from raw images using convolutional networks typically requires more gradient steps, and that in turn results in a much larger cost that you have to pay in terms of sample complexity. And you also pay a big cost in the presence of real-world diversity. One of the things we have to remember about these benchmark tasks is that the same thing happens every time. So when the half-cheetah runs, it always runs in the same infinitely large plane. When you're playing a breakout, the game is deterministic. It always starts off the same way. The real world is characterized by a great deal of variety and diversity, and the more variety and diversity you have, the more experience you need to really master those diverse environments. So if anything, these numbers, the 8 million or the 80 million, are underestimates of the kind of sum complexity that you would need to tackle meaningful real-world tasks where you maybe have a huge amount of diversity, in this case in a robot grasping task. OK, so the challenge with sample complexity. There's a very mundane challenge, which is that you need to wait a long time for your homework to finish. So if many of you experience this with homework 3, with Q-learning, when you're learning from raw images, it takes a while. Real-world learning becomes difficult or impractical in that case. So if you have to, if instead of running your Atari game on a server much faster than real time, if it actually had to run in real time, then you would never finish your homework. And of course, many real-world tasks are constrained to real time. Typically, this precludes the use of expensive or computationally expensive high-fidelity simulators. So if you want to solve a problem where you do have a simulation, but the simulation is not as cheap or convenient as the Atari emulator or the Mujoko physics engine, you would also be constrained by your sample efficiency. And of course, limits applicability to real-world problems. So what can we do? What can we do to address sample efficiency in deep RL? Well, one of the things we can do is we can think about better model-based RL algorithms. So the asymptotic performance of the current model-based RL algorithms lags behind that of the best model-free algorithms, and we can improve that. We can design faster algorithms. So especially things like off-policy algorithms based on Q-learning seem to have a lot of promise to achieve much more efficient learning, but they're also hard to set up, harder to tune, and so on. So there are ways to combine elements of policy gradient and Q-learning. So this is, again, the Q-prop paper by Shishang Gu does some of this. There's another paper called Learning to Play in a Day by He et al., which is a Q-learning algorithm that is much faster on Atari than standard Q-learning that you implemented for homework 3. And they use a particular kind of constrained Q-learning formulation to achieve this. And of course, we can also try to reuse prior knowledge to accelerate reinforcement learning. So we talked a lot about this when we talked about transfer learning last week. We talked about things like the RL squared algorithm, which uses an RNN to try to achieve faster adaptation. This paper I didn't cover, but this is a very similar paper from Wong et al. From DeepMind, Learning to Reinforcement Learn. and then the model-agnostic meta-learning. So these are methods that try to learn in order to accelerate reinforcement learning. All right, let's talk about scale. So if we think about the kind of really impactful benchmarks in other fields like computer vision, things like ImageNet classification or large data sets in natural language processing or speech recognition, they're typically large scale, they emphasize diversity, and they're evaluated on generalization. So nobody ever asked, how well can you classify an image from the training set in ImageNet? Nobody cares about that. Everybody cares about how well you can generalize to new images that were not seen during training. So these tasks, the tasks that are more representative of the real world, are characterized by large scale, diversity, and an emphasis on generalization. In reinforcement learning, oftentimes we test our algorithms on simple benchmark tasks that are small scale, emphasize mastery, and are evaluated strictly on their final performance. So for the ant, it's sort of the converse of the ImageNet task. For the ant, nobody ever asked, how well can it run on stairs after running on this flat plane, because it doesn't make any sense. What people ask is, well, how high is the reward? However, I would argue that insofar as deep reinforcement learning can be useful for real-world problems, it really should move to something that looks more like this. Because really the big benefit of machine learning techniques is that they can handle complex unstructured environments, complex, unpredictable situations that you might encounter in the real world, or if you're interacting with humans on the internet, or if you're handling complex real-world financial data. All this stuff where messy, unpredictable, unexpected things can happen that are characterized by diversity, and where the evaluation is really in your ability to generalize to those unexpected situations rather than really master a very, very, very narrow skill. So where is the generalization? This is something that I think we can do a lot more of. There's a little bit of work on generalizing from massive experience. So I mentioned before this paper from Carnegie Mellon that looked at a robot continuously grasping objects, and this is kind of a similar idea with more robots. We can also look at generalizing from multitask learning, like training on multiple tasks and then trying to generalize or fine-tune to new tasks that we haven't seen before. So I think these kinds of directions are very promising insofar as they'll bring us towards reinforcement learning algorithms that are really practical for real-world problems. So some things to check out if you're interested in this, and I mentioned many of these in the transfer learning lecture, things like policy distillation, actor-mimic algorithm, model-agnostic meta-learning for using past tasks to learn, and many others. And the other thing that is perhaps a very promising direction to explore when it comes to generalization at scale is unsupervised or weakly supervised learning of diverse behaviors. So one of the ways that we can get a lot of generalization in an RL setting is to say, well, let's train our algorithm in many different environments with many different tasks. Let's create many different reward functions. But that gets very onerous after a while. So if you have an algorithm that can actually benefit from data that is collected without very strict guidance, without even having maybe a reward function just for the sake of getting better generalization, then you might make a lot of progress. So there's some work on things like using stochastic neural networks to train for diverse behaviors, reinforcement learning with deep energy-based policies. I talked about this in the Maxent lecture that tries to learn many different ways to perform the same skill, and many others. And I think there's actually a lot more work to do here. I think that we haven't really scratched the surface of incorporating either weakly supervised or unsupervised or diversity promoting objectives for learning behaviors. And of course, generalizing from prior knowledge and experience. So I'm not going to talk about this too much because we had several lectures on this topic, but this is basically all the transfer learning and multitask learning. Can we get better generalization by leveraging off-policy data even from other tasks? Can we learn models that will transfer across tasks? And one question that we didn't talk about, which I think is a really big, outstanding question in reinforcement learning, decision-making, and control in general, is what does it mean to have a feature in decision-making, in the same sense that we have a feature in computer vision? So one of the really powerful innovations in the last few years in vision has been the fact that you could train a big convolutional neural network on something like ImageNet, pull out the features from that network, and then use those features to solve new tasks. So somehow the process of learning on a very complex, very diverse task gave you a representation that is broadly useful for representing the world. Is there such a feature that we can get in decision-making and control? So far, we haven't found what it is, but we have a few leads, a few things that people have explored, a few places to start. One of the ideas is to look at hierarchical reinforcement learning. So if you want to find out about that, read about the options framework. This is basically a framework for producing little mini behaviors that a higher level policy can trigger, and these mini behaviors can be viewed as a kind of primitive or kind of behavioral feature. And this is a citation to a more recent paper that studies this architecture. Another topic that maybe might be a good one to explore to get some ideas about how to get started on this is muscle synergies and how that has been studied in biomechanics. So, for example, there's this work called unsupervised learning of sensory motor primitives that looks at learning an equivalent of muscle synergies for a reinforcement learning task. And you can think of these as basically being transposed of each other. So the options are kind of temporally extended behaviors, and these are not temporally extended, but they couple different degrees of freedom. Yes?
So I would think of these more as building blocks of policy. What about like features of something like an MVP or POMDP that would tell you what kind of policy might be good, or what kind of, for like approximating Q function, would be a good feature of an MVP that you can use to approximate a Q function?
Yeah, I think this is a very good question. I'm not aware of too much work that actually does something like this in an RL-specific way. The closest that I have to offer you as a piece of evidence for the value of this kind of direction is the slide that I showed in the transfer learning lecture from Evan Shellhammer that showed the experiment where what he did is he took a convolutional neural network that was trained to play Atari, and then he cut off the fully connected layers, and then retrained just those layers. And that showed that if you maintain the representation, if you have basically the perfect representation, you get a really big speed up, which shows that there is, in fact, a representation learning bottleneck in these problems. As to how to get those features without cheating, I'm not aware of any good solution to that, but I think that would be a really excellent direction to explore. OK, and the last area here that I want to mention, a little bit as a side note, but something that I think is actually very important and a little bit underappreciated, is the question of reward specification. So if you want to learn from many different tasks, you need to actually get those tasks somewhere. You need to create them, you need to define their objectives. And while a lot of the simulated benchmark tests that we use give us a very convenient way to specify a reward, for example, if you're playing a game, you have a score, many real-world tasks do not make this very convenient. So in some cases, if you're trading stocks, so there's a very natural way to quantify your success, but in some cases there isn't. So if you want, let's say, a robot to pour you a glass of water, defining what its objective should be can be extremely difficult. So you have to learn your objectives or rewards, perhaps from demonstrations, perhaps from natural language specifications, perhaps from watching people, and there's a lot, I think, to be done there to make this easier, to make this work better. That would go a long way towards making RL a more practical tool for real-world problems. OK, so that's maybe the more practical aspect of the challenges and open problems. But now, in the last few minutes of the class, I want to back up a little bit and come back to the kind of ideas that I articulated in the first lecture about how deep reinforcement learning might also help us get at the very fundamental questions in AI about how we can build intelligent machines, and leave you with a few thoughts about open questions there. So in the first lecture, I talked about how we might think of learning as the basis of intelligence. One hypothesis we might formulate is that the way that we can arrive at intelligent machines, instead of designing every little piece of the brain individually and wiring them together, instead we might be able to construct a single learning algorithm that can automatically capture the full capability of an intelligent being. Deep reinforcement learning is a very appealing avenue to explore to study that, because reinforcement learning can allow us to reason about decision making, and deep models can allow reinforcement learning algorithms to learn and represent very complex input-output mappings. So that means that deep models are what can allow reinforcement learning algorithms to solve very complex problems end-to-end, the kind of problems that we usually associate with a high degree of intelligence. OK, but of course we're nowhere near there yet, so there are some things that we can do well and some things that we can't do well. What we can do well is we can acquire a high degree of proficiency in domains governed by simple known rules, things like Go and Atari games. We can learn simple skills with raw sensory input, given enough experience, things like basic robotic manipulation skills. We can learn from imitating enough human-provided expert behavior, things like the car driving examples that I showed. But there are a few things that people are very, very good at that our current best algorithms are just not that proficient at. So humans can learn incredibly quickly, and deep RL methods still are usually quite slow. Humans can reuse their past knowledge, and although there's been quite a bit of work on transfer learning, it still remains a very big open problem without especially dominant good solutions. And it's often not clear what the reward function should be. And it's also not clear what the role of prediction should be in all this. So there's model-free learning, there's model-based learning, and they seem to be fairly distinct things. And it's not clear how, whether these are really two distinct things or whether there's some way to unify the benefits of both. And clearly, humans use actually a little bit of both of those ideas, at least based on the best studies that we have. So what is missing from our current deep reinforcement learning algorithms? And this is where we're going to get to the really speculative part of the lecture. There's a slide that Professor Jan LeCun actually used in his talks that I like very much, which illustrates his thoughts about the problem with reinforcement learning. So the analogy here is that if you are an intelligent being interacting with the world around you, you're getting all this information from your senses. And you can use that information to do different kinds of learning. You can do supervised learning, you can do unsupervised learning, and you can do reinforcement learning. And you can characterize these different kinds of learning in an information theoretic sense. You can say, how much information do you get from every sample? So supervised learning, the kind of very common use of deep learning technology, you can think of it as being somewhere in the middle. It gives you maybe 10 to 10,000 bits per sample. So you have a label from ImageNet. You know, ImageNet has 1,000 categories, so that means that you're getting 10 bits per label of output. You get a lot of input, but you only have 10 bits of output. In reinforcement learning, you're getting a scalar reward function as your supervision. So whatever you learn in reinforcement learning, that reward function is the only thing telling you what you should be doing. And this, you can see this in a very literal sense. If you look at the policy gradient equation, the only thing there that tells you whether one action is better than the other is the advantages. And the advantages are just sums of your rewards. So whatever you learn, regardless of which algorithm you use, it has to come from that scalar reward, which gives you a very small amount of information per sample. For example, if most states are not rewarding, you're actually getting almost no information from those states. You're just getting information from the ones that have a reward. And his main point when he shows the slide is to say that, well, the unsupervised learning, the kind of learning where you're trying to model the distribution over your inputs or predict future inputs is a lot more informative, because there, the amount of information contained in the supervision is the same as the amount contained in the input. If you're trying to predict your next sensory observation, the number of bits in the output is the same as the number of bits in the input. If you're trying to do density estimation, if you're trying to build a generative model that synthesizes images, the number of bits in the output is the same as the number of bits in your input. So here you can have millions of bits per sample. So the analogy he makes is that, well, this is sort of the most of the cake. The supervised learning is the icing on the cake, and the reinforcement learning is the cherry on the cake. This is one hypothesis about why reinforcement learning by itself is hard. So if you imagine, let's say, a scenario where you're not learning to play Atari games where you get a reward function with your score all the time. You're just dropped in the jungle and you're told, okay, now survive. Learn everything you need to do in order to survive. Well, there are many, many different things that you could go about doing, and if you don't receive any kind of indication of whether you're on the right track, if you're doing this thing up here, maybe it would be simply impractical for you to learn the kind of skills that you need to survive in the jungle in a single lifetime. So clearly there needs to be some other source. So where does the supervision come from? And there are a few different hypotheses, and I'm not going to tell you which hypothesis I think is most likely, but I'll just give you three potential ways of thinking about it. Again, not an exhaustive list, but a few potential ways that we can go about resolving this conundrum. So one is the one suggested by Jan LeCun's cake, which is that in addition to reinforcement learning, if we really want to acquire something that looks like an intelligent agent with the kind of with the amounts of experience that we see humans and animals being able to learn from, then we need to think about not just reinforcement learning, but also unsupervised or self-supervised learning that can actually make use of all that rich sensory data without necessarily having to see the outcomes of the actions, the rewards. So you can do this by learning models, by learning to predict the future. You can do it by building generative models of the world. And these things give you a lot to do before you even accomplish your goal. So if you're dropped in the middle of the jungle, maybe you would feel a certain sense of fulfillment if you hunt down the animal and eat your dinner. But even before you do that, just from observing the world around you, you can learn to predict, you can learn your generative models, and that can give you much better representations on top of which you can then acquire the kind of behaviors that you need to succeed. But that's not the only, I think, hypothesis. Another very reasonable way to think about this information and supervision issue is that a big part of how humans and animals learn is through imitation and understanding other agents. So it's perhaps not an accident that some of the most intelligent creatures on this planet are also social creatures. And perhaps pure reinforcement learning really is that hard, that the supervision really is very impoverished, and the way that we can accomplish and learn all the things that we can learn is by watching other creatures, other people, other animals, and so on. So we're social animals, we have a culture, and we have it for a reason, and maybe that's how we can bridge that gap by looking more at imitation. And then there's a third hypothesis, which I think is also very worthwhile to consider, which is that maybe all this stuff is just nonsense. Maybe the fact of the matter is that reinforcement learning is not that impoverished after all, and you can get a lot of information from the giant value backup. Because even though your reward gives you relatively little information, you don't directly try to reproduce the reward. You're trying to actually learn to predict future rewards. And the prediction of future rewards is actually a very complex function. It deeply entangles the dynamics of the system with the reward. And if you look at something like the value function, it'll have a much more complex shape than even a very sparse reward. So perhaps just reinforcement learning is fine. Perhaps the complexity in the supervision emerges from crafting your own supervision by building up complex value functions. So this is sort of the giant value backup hypothesis, that all it really takes is 1 + 1 reward function. Once you see just a little bit of reward, all that complexity emerges by backing up that reward through your dynamics and acquiring very complex supervision in the form of a value function. So maybe it's okay. Maybe all that stuff is just worrying about nothing. So these are a few potential hypotheses. I don't know which one is right, but maybe this is to get you thinking a little bit about how we can have autonomous machines that learn very quickly and very efficiently and can acquire complex skills that succeed under very diverse and varied conditions. All right, so how should we go about answering these questions? One of the things I would really recommend is to think hard about picking the right problems. So we have a number of different benchmark tasks available to us. We can look at, for example, the OpenAI gym tasks. We can look at Atari games. But I think a big part of how deep reinforcement learning technology is going to advance over the next few years is by studying the right problems and not getting too stuck in tasks that maybe don't have the kind of ingredients that will really drive the research towards tackling the important challenges. In fact, shortly after putting out OpenAI Gym, OpenAI actually put out a different suite of tasks called OpenAI Universe, which emphasized diversity a lot more. Since then, this thing hasn't quite taken off, but there are other things you can consider. You can consider working on real physical systems. You can consider working on video games that are much more complex and much more diverse. And you can consider actually tackling the kind of real-world problems that you're really excited about. And the other thing I would suggest is to pay attention to generative models and prediction and other areas of machine learning that might not be directly relevant to designing better RL algorithms, but might be the source of new ideas that might enable reinforcement learning to work a lot better in the future. So remember that there are a number of possibilities for how the challenges can be addressed, and not all of them are about designing better core RL algorithms. Some of them might be about designing better prediction methods, better generative modeling techniques, and so on. Okay, that's it for today's lecture. I'll see you all on Wednesday. If you're watching this online, please do come in on Wednesday for Igor Mardacha's guest lecture. It's nice for the guest lecture for more students to be in the room. You can ask them questions and interact with them. So I'll see you all then.